Hello everyone. Today I'm gonna give you a long review of the paper Axial Attention in Multiple Dimensional Transformers. It's mentioned in Dr. Jeff Dean's 2021 Google Research Annual Report. I think the main contribution the paper offered is the proposal of this axial attention, which significantly accelerate the transformer's computational speed. Take the two-dimensional image input example. Suppose the size of the image is n. Originally, and in each transformer's block, the computational cost is O(n) squared, but in their method, they can reduce to O(n) square root of n. And they say if suppose the input has d dimensionals and the size is still n, and their method can save this amount of computational cost. And you can see if the d is very, very large, and this is, you can save almost the O(n) computational cost. Their task is the sampling task. Sampling task in computer vision. I have to say that I'm not a computer vision guy, so I try to understand the what is sampling by looking at their examples. But it seems to me that it's not very clear. It's not a regression task. It's something like a generation task, I think. Is that something like image compression? Tell me if you're no better than me. But I can understand that this is to using the transformer to convert the original image into a smaller sized thing. Yeah, something like a smaller size or another format of image. And they have some ways of deciding whether the sampling was good. What this is to me, it's very like the BERT encoder, the encoder of the BERT. Because remember the BERT, what the BERT does is the training of the encoder of the BERT is leveraging gazillions amount of unlabeled text data. So your goal is giving a sequence x to xn. Xn could be the word piece, and the question is, what's the next word piece? Just predict this. Okay. It's learning this model, and I think my understanding should be correct. You see, they also had the equation here. Yeah, it's they also keeping talking about autoregressive. This means that they're trying to using all the history data to predict what the next sample data is, and they call this sampling. Yeah. Okay. Okay, now we understand the task. And let's look at the introduction. Okay. They're saying that I liked the writing of the authors. They say the autoregressive architecture could read long range dependencies over a large receptive field, which means that suppose you're doing the transformer, okay, especially the encoder part of the transformer. They call it receptive field, but sometimes people call that input length. Okay, it try to take in all the inputs, okay, to the encoder. It could be word piece in the text, or it can be a sequence of pixels. So imagine that you have an image. You can just using the scanning and converting the squared image into a sequence of pixels. Okay, that's a pixel of image. And also, I work on speech, so you can see that this could be a raw audio samples too, right? Or sometimes raw can be for speech. It could also be if you do short-time Fourier transform, you got filter bank sequence. Okay. Then sometimes the thing is the input length. I mean, this sequence length can be very long. Think about it. Suppose you're handling a video, okay, video of 30 minutes or 1 hour. It could be very long. And same thing to the audio, okay, it could be a 2-hour audio. Text is same thing. It can be paragraphs of paragraphs, and this sometimes makes the transformer is impossible to load all the image or all the video sequence at once because it will blow up the GPU memory. Okay, but the nice thing is that it emits faster log likelihood gradient computation that are suitable for training using SGD. Okay, on the maximum likelihood objective. But this is a straightforward, a good training procedure for generating samples. But the biggest issue, like we just mentioned, is computational complexity. But their axial transformers idea is, like I mentioned in this sentence, it try to allow the majority of the context, I mean, or the history, to be embedded with a higher degree of parallelism without introducing conditional independence assumption. So people may wonder, what is a conditional independence assumption? So I from speech, so I'm familiar with something called a connectionist temporal 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 temporal. It's called CTC. Yeah, everybody knows CTC. For the CTC model architecture or the loss, it has a very strong assumption, which is conditional independence. What does that mean? It means the probability of the prediction output only depends on the current input. So it does not depend on the yt minus 1 or yt plus 1. I think It should be the x1 1 to t. Yeah. It doesn't. Well, this is obviously a very strong assumption, right? It definitely dependent on your history or future. So, and if you make that strong assumption, that hurts your model performance. The background. I think they reviewed the transformer. Yeah. For those of you who are not familiar with transformer, you can search this in my channel. Transformer all attention is all you need. I have a review video of this. Yeah, so transformer, like they mentioned here, you see the calculation matrix time matrix. So the computational cost is O n square, right? And they're talking about their strategy to reduce this computation cost. Okay, so they want to reduce the conditional context and design a small set of data dimensions. So if they can reduce the size n, they can reduce the complexity, right? How they do this? They do not restrict the context, so they get better log likelihood. So if you restrict the context, something like the conditional independence, your model computational is faster, but you won't get better log likelihood because the assumption hurts your model quality. Axial attention. They first talk about axial attention. I think what does that mean? Okay. Suppose you have a channel of the image, okay, or in species spectrogram. It's 5 by 5, okay. Suppose it's 5 by 5, and then you see this is a 2-dimensional matrix. So you have 2 axes. You have axis 1 and axis 2. This is why they're talking about axial tension over axis K. I think they call the row axis 2. I think column is called axis 1. Correct me if I'm wrong. But it's okay. 1, 2, just reverse it. It'll be fine. So they're saying that, sometimes, suppose you're, let me change another color. Suppose you're looking at this row. And suppose you want to generate attention for the central pixel. Okay. This one. So you can either, like they show in the figure 2, you see the row. You can have a full row attention. Yeah, you see this full row. Or you can use a masked row attention. I'll pause the video now and think about why they need they develop this masked row attention. Okay, the reason they had this masked row attention because they wanna apply the causality constraint. So they're saying that because I'm using autoregressive predictor, so at time t, I'm not supposed to know the sample at the t plus 1, or even the sample at the time t. So this is why during training, you want to apply a mask. The mask would set ones here, but set 0 here, 0, and all 0 here. So by setting these to be 0, means that you block the information from these ones. Okay, so the neural network trainer can only see the history and excluding the current pixel, and you force the neural network to squeeze their mind to using their backpropagation algorithm to learn the predicted value at this pixel. Okay, so the goal is to get this pixel correct. And you can see that if you go to the axis 1 or column, you can also have these type of full column mask, full column style axial attention. Pause the video and think about what should you set the value at the red point. Yes. So in this column mask, all the values are supposed to be set to 1 except the red pixel. It should be set 0. Same thing in the mask. This is causality mask. Okay. So you may ask why it's only the left part or the top part, because they're doing these type of I think they also mentioned in the paper, it's called a raster scan. I think this is new to me. Make sure. Yeah, they're doing this raster scan ordering. So what does that mean? It means, so when you want to convert this 5x5 image matrix into a sequence or into a line sequence of 25 pixels, you don't do this in a random order, okay? But you do in this way. You first go through all the columns in the first row, then you go back to the first row, first column in the second row, do this, do this, and do this. So you can see that the prediction is also done in this order, right? So you won't be able to know the other pixels until you reach the other pixels in the raster scan ordering. Okay, this is why you see in the master row and the master column part, it always block the lower rows and the rows on the right. Okay, hope that's clear to you. So axial attention will finish this, and then they also, then after they define this, they start to introduce their axial transformer layers. Remember in the standard transformer, in each in decoder, so it's composed of transformer layers. So each layer has, something like ResNet architecture, linear layer, or especially this self-attention transformer layer. Okay, let's see what's the architecture they have over there. They first define or you tells you the terminology they use, the layer norm, dense. Yeah, I don't think it's too completely for you to understand. Then first they define a feed forward. So suppose you have an input X, then you apply this ResNet connection. So the input X goes to the output, plus you pass You first layer norm the X, then you pass through a dense layer, nonlinearity, then dense layer again. Yeah. I think yeah, I think it's trivial, it's standard, okay. And then you, after this layer, you do the layer norm again. So then what? So then you have the matrix, right? Then you have the matrix. For example, this type of 5x5 matrix. Then you apply the attention K. You see, you apply the attention layer. Sorry, you apply you calculate the attention by using the output of this layer norm. Then you pass through a dense layer and then a ResNet connection. Then you got this type of attention block. Okay. And finally, they define the transformer block. It's attention block pass through a feed forward block. Okay. So you may notice that the transformer block here has a subscript K. Also, attention block has separate K. So it means that the transformer block can either operate on, it does not operate on the whole matrix. It only operates on row-wise. It's called row-wise transformer. Okay. I think it's called row-wise. So you can see that suppose your original transformer it's n equals to s by s. S is, so in this case, s equals to 5, right? And then the traditional transformer, the computation cost is O(n) squared, right? And but in the row-wise transformer, so in each row, okay, let me tell you each row. So the n became, so the si became n. So the computation cost became OS squared, right? And the OS squared equals to n. So this goes to the computation cost of On. So this reduces the computation cost by n, right? I hope I didn't get this wrong. I think so. But I think later on the author proved that, okay, because something like they stack up the previous layers, okay, so the total computation cost would be OS times OS squared. This is O n times square root of n. So although in each row the reduction of the computation cost is On, but in total, after you sum up of all the computational costs, you reduce the computation cost by O, the square root of n, which is, I think, is big if your n is large. Okay, I think let's see more details of how the axial transformer is being done after we see the axial tension and the axial transformer layers. Okay, and then let's see the axial transformer, how it's being composed. This is more like axial. I think it's called axial layers. Yeah, axial transformer layers. Now we're looking at the axial transformer. before we start, they first talk about the row-wise model we just mentioned. They're trying to stack up the axial transformer layers. Firstly, you get the inner decoder. Okay, how it's being done? You can see the equation here. They first they explain their idea step by step. Although the row-wise model is not the model they finally use, but you can see that suppose they have a raw input, and the X, then after password embedding, they got a yeah, X is do this. I want to use this again. So X is like a matrix, and you pass through a embedder, embedding generator. You got the embedding H. Then you want to shift it right and add a positional embedding. What does that mean? So you have seen this. We talk about the causality assumption, right? Or the constraint. They want to make sure that this model does not see anything including this element and the element to its right. Okay, this is shift right does. And if you see the figure 1, yeah, if you see the figure 1, you see here this part. You see this one. You see in, on this row, the 5th row. It does exactly this. Okay. Yeah, then they apply the master transformer block on Axial 2. This is a row, right? So they added the mask here. Actually here, mask here. So this is what they do, okay? And then they multiply over L row. What does that mean? That means they're L row. They stack up the stuff together. Okay. So then they come up with a think about this. Suppose they're finished there. They come up with a transformer. So what do you think the problem is? Pause the video and think about this. Okay. As the author said, it clearly does not define a full context window because they assume that the rows and the rows are independent. So you can see here, so when you predict you predicted this row, you probably could see all the, and it's wrong. So when you predicted this value here, you would get something from here. I think if you stack up all the like mentioned here, L rows, you got all of these. But this is the information you have before you predict the pixel here. So what do you think the problem is? First of all, it does not use the pixels here that you can use. You just throw away the information. That's wrong. The second thing is that because the causality constraint, right? You're not supposed to see this region. This is the future pixels. You cannot use this, and you didn't use this. So what improvement they're trying to do to solve this? Let's see the next one. So this is why they propose the extra part, which is called auto decoder, which aim is to capturing the rows above. Okay, you want to make sure that the current pixel is not only dependent on the pixels in the column before this column in this row, but also to all the pixels before this row, okay, or the previous rows. Okay, if you see the equation, I think personally think it's very clear, but let's see what they do. First of all, this is understandable, right? Pass through the embedding. And then here, it just add the position embedding first. Position embedding is very easy to understand. You just add the relative position of the pixel to pixels, okay? Then you can see here, they apply the transformer block U here for all the upper, and then you can see that in this one, it's not a master transformer block, okay? It is a transformer block of all the pixels in certain row. You see the 2. 2 means XC2. XC2 is a row, okay? But all the rows here. And then it master transformer block 1. What does this mean? Okay, what it means is that you see this is a 1, it's an XC1, right? So it means it would just have a mask for all the rows up to before this current row. You see this one? But it applied on all the upper rows. So you can see. But this one, I think, conceptually speaking, okay, it just get all mask over all the pixels here. That's my understanding. I might be wrong, but I think I got the ideas correctly, okay? And then to prevent the predictor from seeing the current pixel, they shift it down by 1 and they shift it right by 1. This is easy to understand. And they add a position embedding again. I didn't quite get this, but I'm okay with adding the position embedding again. And then the next step is master transformer block 2H. So it means that I think it means that I think it means that they're trying to get the pixels here before this pixel. That's what I think it does. I have to say I might be wrong about this, but I do think I generally get the idea of the authors. And then they talk about their semi-parallel sampling. But this is very easy to understand, and they're saying that this is a squared n faster than the native implementation. I explained the ideas here, okay? And then they talk about the performance. And then you can see that I think this is something like the prediction accuracy, I think. Although they use a bit stem, I don't understand that this metric. I never heard of that before. I'm not a computer vision people. And you can see that their method in terms of the accuracy is the best. And they tried the LSTM. They're saying the LSTM gets slower, so I didn't pay much attention to that one. And they're saying that and I think the above methods, they're either not transformer or the transformer with some a stronger constraint, for example, conditional independence constraint, but they didn't get as good results as them. They also compared on the BAIR Robotics Pushing. It's better. Yeah, the conclusion is that their method is faster. Method is faster, and for 2D image case, they can save the cost by O square root of n. Okay. Thank you. See you next week.